Hi everyone, Mary here, and we're going to talk a little bit about latent heat and changing phase or changing state. Now, first off, let's talk about this word latent. Latent means hidden. If I had a latent or hidden talent for ballet, that means that I could have been a great ballet dancer, but I just never tried. That's the sort of thing. It's in there, but you don't know it's there. When we talk about latent heat is heat that is hidden in a substance, and it's hidden into that substance due to its state of matter. If something is a solid, a liquid, or a gas. And we're going to spend a lot of time talking about water because water is one of the few things you and I see on almost a daily basis in its solid, liquid, and gaseous forms. So when something changes state, that heat is added, but it gets added to do some wild and crazy things, and that's what's going on with latent heat. We're talking about the internal energy of molecules. Now, the internal energy, if you recall, is the total internal energy of a molecule is the total kinetic and potential energy of the molecules in a substance. What is internal potential energy? It's actually the distance between individual molecules. You are familiar with gravitational potential energy. If I have an object and I lift it in a gravitational field, I have increased its potential energy. Here it had a potential energy of 0, and if I lift it, I make it have more potential energy by doing work to it. Well, if you have molecules or atoms that are very, very close to each other, there is no kinetic energy, there is no potential energy between those because they are as close to each other as they can get. But if we separate them in the same way that you separate an object in a gravitational field, you have to do work to separate them. And where does that work go? That work is stored in that distance as potential energy. So when you go from a solid to a liquid, you increase distance. And when you go from a liquid to a gas and you greatly increase distance, you have energy that is basically stored in the position of the relative position of the different atoms or molecules in a particular substance. Now, there are two different kinds of latent heat. One is called latent heat of fusion. The other one is latent heat of vaporization. We'll talk about that in a moment. Latent heat of fusion is the amount of heat that is added or released when something is transformed between a solid to a liquid or between a liquid to a solid. Now, this is one of those vital equations we're going to use for a lot of our practice problems and homework problems. Quantity of heat of fusion is latent heat of fusion times the mass of a substance. So quantity of heat, as always, is going to be joules or calories. Latent heat of fusion will be joules per kilogram, or if we're using smaller units, calories per gram. And mass, of course, kilograms or grams. Now, one of the things a lot of people get confused by, because it says heat of fusion, and if you fuse things together, we think that is when something goes from a liquid to a solid, the molecules fuse. But it's the same number, it's the same amount of heat that is released when something goes from a liquid to a solid that must be absorbed if something goes from a solid to a liquid. So the quantity is the same. You just have to look at the situation very carefully to determine if the material is absorbing heat to melt or releasing heat when it freezes or solidifies. Latent heats are a constant, and you can look those up on your physics constant sheet or in your textbook or online. The physics constants for water, latent heat of fusion, are 3.33 times 10 to the 5th joules per kilogram, or 80 calories per gram. And I give you the calories because we just work with water so much that sometimes it's easier to work with calories than it is to work with joules. And I don't care very often. You use whatever system works for you. Now, one of the cool things about this latent heat of fusion, it tells you that there is an awful lot of heat that is stored in liquid water. And that heat has to be released out into the world in order for something to freeze or become ice. And I think the classic example that I am aware of is the fact that I live in Wisconsin, and I live in a place where it gets very, very cold. And if somebody loses their power or their electricity or heat in the wintertime, a big fear is burst water pipes. And we're taught from a young age, if you lose your power, you need to let your water trickle through the pipes. And as a child, and I remember my parents doing this, I didn't understand why, but there was so much heat stored inside liquid water that as long as we kept that water going through the pipes, it would give that latent heat up to the pipes, to the plumbing, and actually prevent them from freezing, expanding, and then bursting the pipes and causing a very, very expensive plumbing bill. Now, the companion to latent heat of fusion is latent heat of vaporization. This is that transition from a liquid to a gas, or back from a gas down to a liquid. So this isn't a situation where something is near boiling. The equations are twin brothers of each other. Quantity of heat of vaporization is latent heat of vaporization, that should be a little LV, times mass. And LV, latent heat of vaporization, where do you find those? You find those, same thing. You can find these in tables, in your textbook, on your physics constant sheets, of course, or look them up online. Now, you'll notice that latent heats of vaporization are typically like this is 10 to the 4th, this is 10 to the 3rd, this is 10 to the 5th, this is 10 to the 4th. Latent heat of vaporization is bigger than latent heat of fusion. And it makes sense if you think about it, because this is a change in potential energy. If you're going from a solid to a liquid, it's a small change in position of molecules. If you're going from a liquid to a gas, you are really separating molecules, and it's going to take a much larger quantity of energy to have this change in displacement than if you're just going to separate and break those bonds to make a solid into a liquid. All right, next time we're going to come back and we're going to graph these ideas before we do some math with them.